It's my pleasure to introduce Sonia, who will tell us about KLRW algebras.
Thanks for organizing. And yeah, so today I'm going to talk about, well, it can be many things, but the title of the talk is probably best stated as Coulomb branches of quiver. So the entire talk is going to be one gigantic example of sort of a family of Coulomb branches that are particularly interesting, and in particular can be seen very, very explicitly through some sort of diagrammatic language. Okay, so right, so let's sort of recall what we did before. So what's the Coulomb branch? The Coulomb branch is the spectrum of some ring. So this A is well, it can be, I guess I'll just say equivariant cohomology ring. So, and this ring has a convolution structure that gives it its algebra structure. And okay, so for the purposes of this talk, we'll actually treat it as the Borel-Moore homology, i.e. it's dual, because somehow that's the language used by Webster in his papers and slides and stuff. So to avoid me mixing up notations, we'll just stick to this notation. And
is it notation? Oh,
yes.
Additive.
Yeah. I mean, at some point we'll also consider the non-loop rotation version, but this is the most like general version that we'll consider. So, well, as you probably would have found out from the previous weeks, convolution is hard, right? So you're forced to draw these like huge diagrams that spread two boards, and still it's very hard to see explicitly what it is, right? So now our question is, for the specific example of this thing called the quiver gauge theory, which I would say what information it gives, what is the structure on this thing?
T equals T over K.
Well, that's what I have, I think. Well, it can be. I think there's several versions of this.
Okay.
Yeah, I think that,
For G, it's not for G. Oh.
Oh,
yeah.
oh.
Yeah, it's this is GK. If it's GO, it should be this. GO, and then it's like
What is the current like mathematical understanding of the meanings?
So this is what you can think about it as notation and
yeah, and then in reality it means this, but somehow it's more convenient for us to think about it in this form. But really you should be thinking like the precise mathematical version is this.
Does anybody have any ideas to how to make sense out of the left thing? Is any that's like multiple notation?
there is semi-infinite cohomology, which is exactly cohomology for units.
Right.
It's not the direction, it's the same.
Yeah.
Right, I mean, like in worst case, you can just define stuff or steps and shift. You use cohomology for normalizing shift, from horrible stuff, and just see like people do this.
Moving between homology and cohomology.
Yeah, no, I'm talking about the cohomology in with the feature symbolize shift that you can find for affordable objects using systems and shrink full branch whatever. Okay, well, yeah, that's
Yeah, okay, let's just say.
start from Wednesday.
Okay, maybe this makes everybody happier. I don't know. Okay, so the answer to our question will come from so talks that are from 2, 3, 4 weeks before, which is the topic of Springer theory. Okay, so okay, Springer, okay, maybe Springer theory isn't the answer, but Springer theory helps. So so okay, let's do a little bit of a review of KLR algebras, which Larry actually told us about like 4 weeks ago. Okay, so well, actually, this first example comes from even longer. It comes from, I think, Mingzi's talk when he talked about Mill-Hecke algebras. Okay, so one can actually write the relations of the Mill-Hecke algebra in a diagrammatic form that I will write on this board. Expose. So here G is GLN. We need to find y1 to yn as sort of the coordinates of sim. And the simple reflections are y this one. And I don't really, okay, I'll write the relations, but you're gonna see stuff that looks very similar to this in a little bit. And this I basically copied verbatim from Larry's talk. So this is mostly just to show you that all the examples that I'm gonna give in the next hour and a half really all comes from this sort of thing. Hopefully this is correct.
Why generators isn't generated just by dot and cross?
You're saying why these generate the whole algebra?
No, I mean, why do we need so what is the third thing? What is
The third thing is like
those? I think you just wrote something too small. Why is it like just open the cross?
Yeah, this is what we can get just the cross in this one. Or maybe it's the last thing. What's the last thing?
Cross is the no, the last thing is just triple point.
I mean, I didn't really look at this example because I just kind of wanted to say that it was,
Yeah,
this
of
is
course.
where we kind of first see this, but
Yeah,
this might be,
Probably just the.
I think it's just like all diagrams, multiple relations.
Okay. Yeah.
Here for multiplication, like stacking to round.
yes, so, you want to multiply, you would stack them, I think, on top of each other, and the way you read it, it's this way. So, like something like this. Yeah. So,
So they have to have same number of strands or like all diagram, using number of strands.
yeah,
And strength.
Oh, and strands.
yeah, and the strand. Okay, yeah, I did not say. On the strand. Okay. So, the promised topic was quiver gauge theories, so the only thing that I will say about them today is that from a quiver Q, we can take a quiver representation. So more specifically, to each vertex, we'll assign a number vi, and each arrow is going to be so for example, okay, not yet. So for our purposes, remember that we have to specify the information of G and N. So in our case, we'll only be concerned with the case where after we have a quiver, we set G to be the sum of all GLVI, where I is the sum of all the vertices in Q, and N is the sum of all these common spaces. Okay, so then with this setup, G acts on N by conjugation. And so the KLR algebra is the convolution structure on this thing. So, as you might recall from Larry's talk, the torus looks like this. It looks like a diagonal matrix. Okay, let me just close one more. So, and if we consider, okay, so how the KLR algebra is constructed is basically considering the ordering of the size of these entries. So within each block, with the same first index, we must have I TI1 is smaller than TI2 and so on. So then that gives us the size. The size of the entries gives us let's say a word of length the size of the units. So for example, if I have I don't know, if I have something like T11 is smaller than T21 smaller than T12, then the corresponding word would be 12. Wait, okay. No, that's not right. Well, okay, I guess this also makes sense. Yeah, so this is how we kind of construct this word, and this is gonna be like the starting points of our diagram when we lay them like on straight. So the generators I guess here equally something about this to be more consistent. Gee. So we can see the generators through these diagrams. So for example, if we have yeah. Oh, yeah.
What was you?
Here is you. You was like some yeah, it's some B stable set.
There's some
Subset of
full vectors where the weights with respect to this weight given by the sequence it gives you. I mean, like it's essentially 1 here and -1 there, and it's -1 should be over.
So okay, let's take our example there where we started with 1, 2. So if these strands are labeled by 1, 2, 1, then this would be corresponding to the generator T21. And we also have stuff that looks like, can't see the color now. Let's see. So these are what I think Larry called the size in his talk. And there's also stuff that looks like this, which he called R. Or did you call them that?
Yeah, I think it's wait, no, it's these are just.
Wait,
Is it
so the
the
other
opposite?
way.
R is multiplication by something.
Just side because to go across different spaces.
Okay, I mean, I haven't really said, what
Yes,
this action, like, the action is. The action is multiplication. By T here, and then here I think is the divisor operator, and then here is. You know, these sets,
Can you leave for
Or
the
is it
same?
the other one?
Yeah,
what? The other one?
Yeah, sorry, maybe I messed up last day, I'm sorry.
Seems so.
Wait, yeah,
Now we have to also change the text.
this- okay, that's actually good, so.
Sorry, saying.
And then it's modulo a bunch of relations that I should write because they will be exactly the same relations that we follow an hour later with this one. So relations are this. Here because maybe I shouldn't be. Then it's this. And it's the other way. It's so. Then there's the last one is stuff that looks like this that I don't really want to say, because it's fairly horrible, but we'll cancel this. We'll just say, but. Okay, let me, denote this thing in the like, then this is. So, some very complicated way of untangling this, but basically, the good thing about this is that you only have to think about moving dots through crossings and potentially resolving stuff like this instead of drawing like convolution diagrams and figuring out what I think is harder stuff. So
So we,
yeah,
if, so in words, the only interesting thing happens if I equal to k, but not equal to j, in which case we should take this difference. I think it should be like ck. Yeah, I think it should be just the t's corresponding to the strands.
well, it's very possible that one or more of these things are wrong.
No, it looks good, but just
I don't know.
just like tk something, tj something, ti something. Just whatever variable corresponds to each
Yeah.
string.
So.
Okay, so
Yeah.
here it's not non-zero only I equal to j, right? Oh, I equal to k.
Yes.
I is k, but you have non-zero a minus I, isn't the zero in this case?
Oh, yeah. That's true. I don't. Actually,
Another line, yes.
Oh,
There is-
different roots.
there is.
There are like,
Yeah.
yes,
Oh,
yeah.
important.
Yeah.
I mean, these are two different variables of the same color. Ti 10 and Ti 11. Subtract two polynomials in two different variables and divide.
Oh, I see.
So anyway, that has zero no negative.
Yeah, it's probably better to know that something like this. So it's not like.
I guess weights rather than.
Yeah. It's good. Notation for this. Something like this. It's not, it shouldn't be zero. Hopefully the indices are right.
Like strength on the left, strength on the right. Divide left on the left. Dot on the left minus the right.
So. So now let's. Okay, now let's actually get into it. So next we'll consider a slightly more general case of that actually, which is in our setup. Instead of defining xu to be that, we'll replace the Burrell by P, which is P a parabola. So okay, this gives us what's called KLRW algebras. Oh God. That took much longer than I thought. Okay. Okay, so instead of defining xu to be that, we're now defining xi to be kind of basically the same thing, except that we've done this replacement. So what we'll now consider is the ring I cross, which is called the Steinberg algebra. So, okay, so there are a couple of sort of obvious generators of this thing that take the shape of these, right? So we can talk about okay. So question generators. Well, there are a couple of obvious ones. You can define R of ui uj if ui equals pj. We can also define the psi I to be this thing if ui is p varying and PI is E. Well, but then now the second question is, does this generate everything? Sadly, the answer is no. So what are we missing? Did I write a number? No.
Psi I is class of
Yeah, it's a class of that thing.
inside, it should be inside xi cross xi.
Yes. Wait, it should be inside, it should just be inside. Wait. I mean, it should just be inside xi, right? Because xi is like already this product. But where does x psi I sit inside? I remember how this one. What the answer is.
The fourth size were in like the diagonal components.
Isn't that xi plus x over n?
Is it? I mean, it should be, because like it's the generator of that thing, so it should like.
Yeah, so.
Yeah,
So
it should
R wouldn't be.
be
Yeah,
graph of lab, someone to some person, not a graph.
so I guess you wouldn't say PR equal PJ there, I guess.
Well, yeah, I think here we should change the order. This side we should change the order.
There should be two different things, but. Um,
I guess you're right, that that's H star PJ of. Like as long as you kill one for freedom, and then you can write things like that, I guess. It's very nice. Like second component and plus.
I mean, like, the point of this is to say that they don't generate everything, so they're not supposed to account for all the cases, and I think. If you define psi, you do assume that I equals j, I think. Yeah.
What is use of I in this case?
It's a PI invariant subset of n.
Thank you.
So maybe, okay, maybe when I say it over more, just like, hopefully this makes more sense. So, okay, so, let's construct the rest. Okay, our stuff. So let H be the normalizer of G inside GLN. And this thing has a torus TH with the algebra small TH. And then this thing has a real subalgebra PHR. So the thing we want to know is that this thing, much like that from before, this acts on n by diagonal real matrices. So in order to sort of solve our problem, well, let C be a convex subset of THR. That's closed under the Wild group action. Then inside here we'll have a smaller subset C0 where P, I guess Px is where X is like one of these matrices. So if we restrict ourselves to only looking at pairs of UI/PI, where that doesn't grammatically make sense. If we restrict ourselves to these pairs of UIs and PIs that appear as UX PX for X in this convex subset, then the Steinberg algebra is generated by so yeah, so that's this basically tells us if we restrict our view of these UIs and PIs to this specific like convex subset where this kind of returns us to our previous case where PX is a real, then the Steinberg algebra is actually generated by what we get. I don't know what EI is.
Okay. Also, what is C0?
C0 is this subset of a convex subset of T where your like the parabolic is a Borel.
Yeah. How do you how do you get a parabolic from the point?
Well, I think so. I mean, I had the impression that they were sort of ordered by like whatever index, and you would just like
representation of that way, right? Then you'll go with the.
No, but it's I mean it's not integer. Yeah, I think universities businesses to again use this as a call weight to see who has positive and who has negative, and then they propose some. But this H is equals to this.
It almost even like more certain means as well, that but that is normalized it is page.
Yeah.
So is there a difference between this its torus and that just maximum torus on the right board for the entire KLN?
I don't know because I haven't actually like computed explicitly what it is because I was sort of less concerned about this part of the talk, but maybe I should have like checked what it actually is. Okay, so I do have more. Yeah, so okay. This part I forgot to do, but basically, okay, this thing is we define we first define UX to be the subspace where X has the weight greater than minus epsilon. Well, basically like positive weights for zero. So then Px is maybe this makes more sense. I think it's exactly what you were saying. Where you kind of pick out the positive weights of this X and then just define Px to be what's the corresponding parabola.
Greater than.
Well, I guess it like acts by. That's actually a good question.
Maybe the element equals X by a bunch of numbers.
Yeah, it should
Yes,
act
there
just
is
by
also,
numbers, right?
All the children.
I mean, this X is inside T. So it acts by diagonal, like it acts like diagonally by a bunch of numbers. And I think this is, yeah, this is like the number.
For each X, you can see that this would be like this directions.
And so instead of parallel to our own, it's not really, the UX is just zero.
Mm. Well, I think it's non-zero on each fundamental.
Yeah, it should be
It's
non-zero.
on each way inside of vertical zero. And it's zero.
So, okay, I'm just kind of gonna claim the rest of this part of the KLRW algebra because to really say sort of in detail what and why this is true is very difficult beyond me hand waving and saying this for L means that we kind of get the same thing. So what this means diagrammatically. So remember, did I just erase it? So we just have a quiver Q, and to express this Steinberg algebra in like the KLR language, we'll have to add framing to our quiver. So here we're now considering n is the sum of the negative I of what we originally had. And also plus additional sort of framing information. Um, So for so
Is your arrow from W to V or? If it's from W to V, why is from C V I W I?
or did I just completely mess up the arrow direction?
I think all your forms are reversed, including the. Oh, sorry, it's.
I mean, it should be point, I mean, it should be in the other.
I don't.
I think it's from, if it's from CVI to CVJ, then the arrows from microchain. At least, okay,
Oh no,
I don't know, maybe,
that's bad.
no, maybe Americans were different, I'm not sure right now.
Give me 1 second, I can check it quickly, I think. Yes, let me screw this up. Because it should be. Yeah. Yeah, and somehow I had it in my brain, that was the other way around, but it actually is not. So yeah, so. Okay, where did it? So. Here. Now, instead of sort of just having black dots on a line, well, in this case, white on the blackboard, dots on a line, then we'll get a VI tuple that's black. And a WI tuple, which is red. That the red part is for the fragment for each eye. So the rule is that red lines are straight. So they can't twist through the other, like it can't have stuff that's like this. You can't have stuff like this. It has to go like straight from, I just have an eye to an eye that's red, I just go straight from here to here. So. And then everything as before. Oh no, I forgot to push it here. Plus, a couple of other relations relating to the, related to the red strand. So. This is. So. So. Really. The only thing we kind of care about is that, well, what is this and how does this relate to our fiber algebra? Well, if we pick C equals to T plus theta for theta some, I think some translation. Then the KLRW algebra, which is the above thing, C of all the diagrams, more relations of the current number. So. Yeah, so that's basically telling us that if we kind of pick and choose correctly, that this gives us a very nice way of telling us how multiplication works. Well, I guess convolution. This gives us a good idea of the algebra structure. This fiber algebra, which will serve as a sort of finite dimensional model for our thing. Oh God. Okay.
Who's all, who's all here?
Wait, what?
C is T plus all.
I think it's just some sort of translation factor that you can like translate T.
Oh, sorry, T and then T stores.
Yeah, and then you can,
Yeah.
you can still get kind of the same thing, but I mean, in particular, if you take T, like, if you only restrict yourself to looking at T, then that's. So, oh no, is it? Okay, maybe it's not this. Okay. So finally, we're into what I wanted to talk about today, which is the infinite dimensional case. So, well, historically, these KLRW algebras were kind of already interesting for their own reasons, but this is a Coulomb branch number, so we'll kind of explain how this ties into Coulomb branches. So, in the spirit of continuing to replace our Borel with other things, here. Okay, so now what we're considering is that thing where we had something that looks like this. So we want to understand this thing. And so we kind of try and run exactly the same thing as before and try to see what we get. So we'll now define the equivariant subgroup is so the equivalent of the Borel subgroup, basically. So so, well, parabolic subgroups kind of become let me not say definition. Parabolic subgroups are kind of equivalent to things called parabolas. Although I don't, well, I guess I kind of have narrowless, so I don't know say anything more about this. So. Yeah, so. Our string of theory is now this thing. Where, we kind of have the, I guess, the obvious generators. As before. So this sort of graph function that acts by W and W hat, where now instead of a wild group action, we consider the F on a wild group action. So now let's consider the same torus TH1, where things are now up to translation.
Yeah, sorry for
Yeah.
question. So to me, say parabolic separate become parabolic. Can you like do the same thing but replace B by P in the bottom
Yeah.
left of that diagram?
Yeah.
And we get some other thing instead of that.
Yeah. Yeah, I should probably.
So it's not, I don't very lost with it. Like,
Yeah.
why I is not, is I just like B double correct? Or why is
No.
Below the triangular, you can have stuff divisible by the Z.
Ah,
divided to-
Oh, I see.
So you just have to go to 0 and then instead.
Oh, I see.
So it's nice to know this.
Yeah.
No more.
What?
Yeah, sorry, what is that? Sorry.
It's a pre-image of B.
Oh.
This map.
Wait, I think the definition is that you just have to contain a conjugate of equivariant. In particular, you don't have to be contained in GT.
Right.
Okay.
Just P contains some conjugate of phi, and I think that's what we'll use. Or maybe not.
I mean, yeah, we don't, I mean, the reason I kind of glanced over it was that I don't really necessarily want to be sort of functions.
Yes, you understand.
Probably, I don't think it's very like conducive to say anything about this because we won't really use it that much. It's just to say that we kind of have like the equivalent thing for a Borel is the equivariant group, and the equivalent thing, like the role that parabolics play in the finite dimensional case is replaced by these parabolic things, which contains the Borel and it has all the nice properties that we want out of it, and I think that's all like I need for.
That's the difference. It's just the usual cube with the parabolic and instead, right?
Yes, yes. Yeah, that's one of the questions Elkanan asked me. Sure, I mean, that's the claim. Sure, of course not. It's not available for that. It's not available for
There are like way more parabolics. And
Yeah.
Yeah.
All right, so. Now we're considering the torus up to translation, so. So our root spaces. Are of the form here. where let's move out. This by basically alpha acts by itself and then n just acts by transition. So here we take C equals 1. So or do the same kind of use C twice. So let's see let me just say that we can also define ux px as before. And consider T1 is 5, which is T is 1, but up to translation by 1. So then here we can also define C as before, so convex. Goes under FIR and also further C0, where as before we had that our parabolic px was below. Here our parabolic px is the equivariant. So okay, so maybe I should like tell you that here we kind of draw the same conclusion where our Steinberg algebra is again generated by the same things. Yeah, so I guess the running theme here is that everything is just like grossly generalized Springer theory. So we started with the most simple case where we only considered like quivers. And then we wanted to replace that with the parabolic subgroup, and then we jumped to this infinite dimensional case. But then they kind of all have the same structure when we think about the right subset here. That's C0. Okay, so if we take G to be the same thing. So from quiver we have G equals so GL of VI, where VI is the number attached to each vertex, and N is the same thing. To J. So. Let me try to say. Okay, so now, recall that here we considered now our torus is something that's up to translation by one. So what you might imagine is that picture we draw is no longer points on the line. But points on the circle. So Yeah.
After translation by one, does it mean up to translation by one times C in the torus? Or, but it's like the torus for that, I'm.
yeah, I mean. Yeah, translation by well, it's like this factor is like translation by the areas. You just keep translating it, and it should all be infinity. But you kind of want to keep it to the interval 0, 1.
Perhaps he used this while like the element of while loop in the hero adjustment, but just dimensionally roots to shift like each time you get something in you choose a chamber, translate everything inside it, and it's fine about the direction, the whole part of it is shifts, which become this.
Yeah, it's absolutely fast, right? That action. So okay, so yeah, so okay. Take C to be the same thing. Then a point is in C0. And the black points are this thing. So then the dominant. Okay, I guess this is kind of. The dominant. While chamber. Has. This is the action. By. One. Mouse thing, this thing. So this is how we keep points within. Everything. 0, 1. So now, okay, so our points can lie on a circle, so. Instead of having a square, we kind of rolled it around like this. So now it's calling a cylinder. Right, so. So that's kind of exactly the same. Okay, so let me say what's on there. So what's on here is, again, red straight lines. Black, possibly curves, and black dots on curves. So relations, the same thing, except that now they're kind of wrapped around the cylinder instead of laid on a square, or like a rectangle. Well, I guess like R. But then there's like finitely many points, so then, yeah, same as. So, yeah. So, yeah, so now we've, yeah, so the point of doing all that was to say that this version is cylindrical. KLRW algebra is isomorphic to H K XI K.
Okay.
So with generators. So. Um. They are not the same INJ. Okay.
It was in lists. It was. I'm just on that retirement to a certain order of the structural order.
I mean, you kind of just like. I mean, kind of the stupid answer I would give you is that it's the same, like it's the analogous thing to the finite dimensional case where you just have xi equals g plus p. So here I would have xi. Okay, I need to use some other notation. Well, no, I already. Okay, so this was the finite dimensional case, and here we're kind of using notation and kind of referring to exactly the same thing, except that here I think we're taking G to be. But I don't really know how to make sense of this thing.
UI starts with MO and then changes if you go if you stress cross or something. So UIs are also for a four invariant
Yeah.
some representations and key.
But in this case, in other words, three and other ones we get are taking three innings of the finite type parabolic associated with that.
No,
So then
I mean, if you start doing something like, I mean, before you shift, I mean, when you shift by T, of course, you get something. But at least in one purposes, example, if you go really far T direction, you just at some point you get pi over 10, and output get 12 over 10, if you are conjugate.
So okay. well, I mean, the way I understand it is like some sort of iteration of like all the parabolics, but that might not be correct. Cause in the finite dimensional case, it's very clear in what I is, but I don't really know.
Yeah, but another thing, but it's how is the xi and c related to our Coulomb branch?
That is exactly what I'm about to say. Yeah, so, okay, so we kind of did a lot of nonsense about stuff, but let's go back to the topic of this seminar, which is the Coulomb branch. So our goal is to sort of see these Coulomb branches in this framework. So recall that we have a Gn is equal to Go. So in particular, okay, so in particular, this corresponds to our previous case, when px is GO. And yeah, so to do this, want to consider X to be a scalar matrix for I can't read where I go. So yeah, so I mean, I'll admit I was kind of confused as to what this is, but it's very easy to understand diagrammatically. We want to basically pinch all of the same buttered strands. So for example, if I have this and I have let's say I'll use your I have something I also IGI bottom. It's probably easier for me to draw this if it's IIJ. Okay. So then what this means is that if I originally have something like
it's just
then what I want to do is to basically combine these two dots and combine these two dots by sticking them together. So the Coulomb branch corresponds to the case when I have this. Yeah, so this would be if I had like some. So the way to draw the Coulomb branch like algebra diagrammatically is to first draw the corresponding Steinberg algebra version and then pinch the necessary vertices together, which are basically all vertices of the same color and the same letter together. So. Yeah, so then, but then it would still follow the same relations as before. So,
So now you have this sort of points where like there are 5 strands hit. And
yeah, I mean, okay, so the way they draw it is slightly nicer, where you just have one strand hitting it, but they kind of extend it and then just have them hit somewhere that's away from the boundary, so it looks less. I mean, I just draw it very crudely because really it should be something like this, like where they meet at some point and then just one strand hits the point.
But it's some sort of funny little picture that looks like, kind of K inputs and then.
Yeah. I mean, at this point, yeah, you'll have stuff that's like this. Yeah. Okay. I don't think I have time to say anything else.
Well,
I mean, I have to go.
So, to go.
Yeah, I have to go. Like I would take more time, but I kind of also have to run. So, yeah. I'll send notes with. I was planning to talk about an example, but yeah. Okay. Well, yeah, I guess I'm just gonna leave it at this. Thank you.
Any questions?
Like, so like, the picture, you have some like black dots and red dots and whatever, so probably the number of black dots is like the sum of VI. And the number of red dots is like.
Some of WI, yeah.
And, but how do you base them on the first?
It's by the relative order of the like matrix entries, because this thing. Well, originally this thing acts by like diagonal root matrices, but then there's already some restriction on the order of those entries, like the size of those entries, because within each block of TI1, they have to be in ascending order, like within each block. So then the overall ordering of all the diagonal entries of this matrix will form the order of like this stuff on the circle. So if I have like TI1 is less than T2 T2. So exactly what it is. So then it could correspond to dots in the order IJ. So when you kind of incorporate the WIs the same way, and then do that, and then come to this.
Or like, it's still because of like, so in order to get second order, and what choice do you make? It's no choice.
I mean, that's a choice of this X, right? Because X is some element in T, it goes here, like T. Oh, okay. And then so this thing acts by this matrix, and
I see.
choosing according to this action, I have a matrix, and then this gives you some ordering of the entries, and that order will be this dot order.
And you said that to get T of O, we should take a very particular choice of character, right?
Yeah, so, yeah, you'll have to take this, but I'm somewhat unsure about what this is.
It's just like no.
Yeah,
Zero.
like I think no zeros, you're just,
Ah, so that's
yeah, I
T,
guess
so that's-
that's it.
Only power 15. I can get nice power 15, but.
So since I also require no active power.
Yes, because everywhere here there's some like powers of t that you can get additional amount if you want. You have to big, you have to expand, if you have to small, but here it's just kind of in the middle, so exactly condition that you want is all the series. Okay, no questions, yes,